be knowing there is a wine and cheese party in this particular tower. You know, there is a tall tower attached to this particular complex here. That is called the Gamma Tower. And the party is on the 11th floor of the Gamma Tower. In order to access it, you have to enter from one of the side doors of the tower. The side door is on the street level, and you have the code in your packet that has been given. So you punch the code, you can enter, and then go to the 11th floor. Okay.
Okay, so welcome to the double feature of this afternoon. So this morning I explained pretty much one side of the AdS CFT correspondence, namely the gauge theory side. And so now this afternoon I have the more ambitious task of actually explaining the second side, namely the superstring side, or in its low energy approximation, the supergravity side. So before we do that, I just want to be on the same page with everyone and briefly remind us all of the structure of spinors and of supersymmetry in general dimensions, because after all, the string theory we'll be dealing with, and also the supergravity, will be in 10 dimensions, so we need to know how that works. So I'll start with spinors in general dimension. So the dimension of space-time is d, and the signature is minus plus plus plus. And the Lorentz algebra has these generators as usual and satisfies this relation. So now you all know from the Clifford algebra how to construct the spinor representation for any dimension. And this is the Dirac spinor representation, so it may or may not be reducible. In the case of odd dimensions, if d is odd, then this representation is in fact irreducible. But when d is even, as for example in 4 dimensions and 10 dimensions, then the Dirac spinor is actually the direct sum of 2 Weyl spinors, which I'll just call S plus and S minus to give them a definite name. And you all know how to do that. You use, in fact, the generalization of gamma 5, which I called here gamma bar, to arbitrary dimension. And this object anti-commutes with all the gamma matrices, and as a result commutes with the Lorentz generator in the spinor representation. And since this matrix is not the identity, this means that this representation must be reducible. So the reality properties of S plus and S minus depend on the dimension mod 8. I'm only here going to work for dimension which is even now. So if the dimension is 0 or 4 mod 8, then S plus and S minus are complex conjugates of one another. So that's the case of 4 dimensions, where the right Weyl spinor is actually a complex conjugate of a left Weyl spinor. But in the dimensions other than 0 and 4, namely 2 and 6, S plus and S minus are self-conjugate and real, or pseudo-real. And there is another condition one may impose with Lorentzian signature. This condition doesn't exist for Euclidean signature. And that is the condition of reality. But a real spinor is not a Lorentz invariant notion. So in fact, one needs to make this Lorentz covariant. And the right thing to do is to define its charge conjugate in this way. And the Majorana spinor is then defined as a spinor which is its own self-charge conjugate. And this is possible in dimensions 0, 1, 2, 3, and 4 mod 8. And in fact, it is possible to impose both conditions at the same time if the dimension is 2 mod 8. So that means in 2 dimensions and for our purposes in 10 dimensions. And so this is a condition that reduces the spinor further by dividing its dimension not just by 2, but actually by 4. So that's spinors in general dimensions in a very brief review. So equally brief, let's now move on to supersymmetry in general dimensions. Now, this you could mathematically do in any dimension, but in fact from physics there is a very general rule, I'll just say, theorem if you wish, which is that you cannot have a theory with interacting massless fields of spin larger than 2. This was shown in a paper by Weinberg a long time ago, and has to do with the fact that for such fields, you couldn't construct an energy momentum tensor that has reasonable properties. Now, of course, we know that spin 2 better be allowed, because that's, after all, the massless graviton. So in fact, when we discuss massless multiplets, we will limit ourselves to multiplets that have spins no higher than 2. Now, this is a relevant criterion here, because as you remember, the supersymmetry generative changed the spin of a field or of a state. And so the limit on the total spin is actually a limit on how many supersymmetries you can have. So now let's work out what that is. So I'm going to be interested in a massless multiplet, which in fact will be the supergravity multiplet. String theory, of course, has also a lot of massive states, but there is no limitation there. You can have massive states which have any spin. You should just look at nuclear physics. There are all kinds of spins, and all these particles are massive, and that's perfectly fine. So in fact, let's assume that we have supercharge if Q alpha I runs still from 1 to n, but alpha now is some spinor index, whatever it might be appropriate for this dimension. So in general, it would be a Dirac spinor, but in fact, you could also reduce this to a Weil spinor, whatever that representation S is. So now we again consider massless representations and play the same game that we played this morning. We pick a light-like vector, and again, the supersymmetry algebra actually splits in this way, where 4E is now multiplying the identity matrix in this Weil spinor space, which is half of the Dirac spinor space. So you see that, again, in this representation, half of the supercharges effectively vanish, and the remaining charges can be viewed as raising and lowering operators for all the states in the representation. So how many are there? Well, in fact, there are as many as half of the dimension of S, because the other half were killed, just as we had them killed in 4 dimensions. Now, half of them are raising and half of them are lowering. So in fact, that means that a quarter of them are raising operators, or a quarter of them are lowering operators. And this is to be multiplied then by the dimension, by the number of spinors, by the number of supersymmetries you have, n. Now, if the helicities range from -2 to 2, now I know that I'm not strictly speaking in 4 dimensions, so the notion of helicity, well, does not immediately generalize to higher dimension, but there is actually something that plays exactly the same role, and that is the height of a weight in the representation. So the helicity essentially ranges from -2 to 2, so the maximum should be 8 raising operators, because in 8 steps can I get from helicity -2 to helicity 2, and I should not be able to go beyond that. I should not have a multiplet that's longer than that. So if a quarter of the dimension of S times n is less than 8, that's equivalent to n times the dimension of S being less or equal to 32. So basically, if we look in various dimensions, and find out what the smallest dimensions of the representations are that I can have for the spinner, then in fact I have a handle on how much supersymmetry I can have in each of these dimensions. So, well, what would be the biggest spinner representation that has dimension less than 32? Well, this actually occurs in dimension 11. In dimension 11, the Dirac spinner has 32 components. The dimension in general is given by 2 to the integer power of d over 2. And in fact, if the Majorana condition is imposed here, then we have exactly 32 real dimensions. Another possibility, if we go down in dimension, if d is equal to 10, but then I can impose the Majorana-Weil condition, so actually I can make the spinner even smaller, and this in fact allows me to have n equal to 2 or n equal to 1, and so on and so forth. So this slide gives you the reason why in various dimensions the number of supersymmetries is bounded, and why in fact beyond 11 dimensions you cannot have Poincare supersymmetry realized on massless states. Okay, so now we of course will want to move between different dimensions, and this forces me to briefly discuss Kaluza-Klein compactifications on circles. So here, if we take a d-dimensional flat space-time and compactify one of its dimensions on a circle of radius r, then we want to analyze basically what happens to the various fields in the theory, and also we want to know what happens to the supersymmetries in the theory. So we're going to assume that r is sort of a small radius of this circle. So the first case is if we consider a bosonic field with periodic boundary conditions on this, then in fact we can expand the full field on d dimensions in terms of the field on d minus 1 dimensions. That coordinate I'll call x with a mu bar to indicate that its range is from 1 to d. And then if I call the coordinate in this circle direction y, then in fact I have a simple Fourier expansion in that direction. And if we look, for example, at the behavior of a typical kinetic term for a scalar, for example, or for any bosonic field, then what happens is that the D'Alembert reduces to one lesser dimension, but adds to the mass a term which involves the square of the momenta on this circle. So as r goes to 0, all modes except n equal 1, except n equals 0, actually become very light and decouple from the theory. So if the mass is also small, or actually in our case 0, the only mode that survives is actually the 0 mode corresponding to n equals 0, which means that it's that part of the field that actually doesn't depend on the extra coordinate. So this is the basis for Kaluza-Klein compactification. And for a scale of field, this is of course very simple, but we need to do this also for an entire multiplet, for example, of supergravity. So how does that work? Well, first of all, if we have a bosonic field but some boundary conditions which are other than periodic, then there are no 0 modes, and then all modes become very heavy and actually decouple, so that in the low energy approximation there is nothing left at all. Now, if we have more general bosonic fields than a scalar and still periodic boundary conditions, for example, a vector field or a tensor field, then the procedure of above essentially applies, but the tensor index also splits according to the decomposition of Rd into RD minus 1 plus this extra circle. So that's what I've denoted here. So here is the index that has components ranging from 1 to D minus 1, and then here is the extra one. Okay. Now we apply the Kaluza-Klein reduction of the previous page to this, and so all Y dependence disappears because we have periodic boundary conditions. And so what you see is that we have one field left over here, which is a vector field under the Lorentz group in one lesser dimension, plus a scalar. So more generally, if I have a tensor field in some representation T of the Lorentz group in D dimensions, then under a Kaluza-Klein reduction on a circle, this decomposes into the direct sum of all the tensors that appear in the branching rule from the Lorentz group in D dimensions to the Lorentz group in D minus 1 dimensions. So for example, for the metric tensor, which represents the graviton, we obtain, the first one is a scalar, the second one is actually a vector of one lesser dimension, which is called the graviphoton, and finally there is the metric in the lower dimension of dimension D minus 1. Also, if you have spinor fields with periodic boundary conditions, then similarly the spinor of the larger Lorentz group decomposes in a sum of spinors of the smaller Lorentz group according to the standard branching rules. So that actually means, if we summarize this, that if we have boundary conditions that are periodic on all the fields, bosonic or fermionic, they will reduce to simply the zero modes in one lesser dimension, and the representations of the Lorentz group simply decompose according to the branching rules of the larger Lorentz group to the smaller Lorentz group. In fact, you can see that because of this, for every boson there is a fermion which, supposing that I have supersymmetry in the larger dimension, then for every boson there is a fermion that is also compactified, and so in fact all the supersymmetry is preserved. The number of supersymmetries, if you Kaluza-Klein reduce by periodic boundary conditions on a circle, is completely preserved. So that's good to know, because in fact this allows us to start from the most unique supergravity theory and then construct lower supergravity theories. So, of course, recall that in the Maldacena correspondence, I had stated the equivalence with full string theory on AdS5 cross S5. But that's a subject that's not that well understood yet. So what I'm going to do is begin with the discussion of supergravity, which is the low energy limit, and then we'll discuss strings. So the most unique theory is the one in 11 dimensions, where I can only have n equal 1, and there is a single supergravity multiplet which contains the metric, the antisymmetric tensor field of rank 3, and the Majorana gravitino. And since this multiplet is massless, I've lifted here the little group, which in 11 dimensions is SO9, and all the physical states of the theory form irreducible representations of this little group. So the metric, there are 44 states, there are 84 of these antisymmetric guys, and there are 128 of the gravitino guys. And in fact, you can see that the sum of the bosonic number of degrees of freedom is 128, and so is the sum of the fermionic degrees of freedom. So there is a match between those numbers of degrees of freedom. So this theory was discovered 30 years ago by Kremer, Julia, and Scherk. And now, by simply applying dimensional reduction on a circle a la Kaluza-Klein, I can immediately reduce this theory to a theory in 10 dimensions. And the number of supersymmetries is preserved that number is 32 Majorana supersymmetries, and in this case amounts to having also the maximal supersymmetry in 10 dimensions, which is an n equal 2. That means that there are actually 2 supersymmetries, each of which are a Majorana and Weyl fermion at the same time. So here is the collection of the multiplets. So as we saw, the metric reduces to a metric in lower dimension, plus a scalar, plus a graviphoton, which is this vector here. And then the antisymmetric tensor of rank 3 reduces also to an antisymmetric tensor of rank 3, plus 1 of rank 2. So that's this thing. And similarly, this fermion, which has an 11-dimensional Lorentz index, reduces also to a gravitino and a dilatino lambda. So the 11-dimensional theory was parity conserving, and this 10-dimensional theory is also parity conserving. Now, actually, in 10 dimensions, there is another theory which has the same number of supersymmetries, namely 32. So it's also an n equal 2 theory, but whose bosonic field content is arranged somewhat differently, and also its fermionic field content is a little bit different. There is still a metric in the same dimension, so the same number of degrees of freedom. But now instead of having a single scalar, there are actually 2 scalars. The scalar is the dilaton, the other scalar is the axion in 10 dimensions. And here we don't have a graviphoton. On the other hand, we have an antisymmetric rank 2 tensor in addition to the one that was already there. So we have 2 of those. And we have a new field, the antisymmetric rank 4 tensor. And that plus on there means something that I'll explain in a while, that its field strength is self-dual. So it has 2 different gravitini, because n is equal to 2. There are 2 kinds of those. In the parity conserving theory, the chiralities of these 2 fermions was opposite to one another. That's why it's a parity conserving theory. But in the type 2b theory, these parities are actually the same, so it's a chiral theory. So this theory is chiral, and in fact, this is the theory that that gives you the arena for the Maldacena equivalence conjecture, the type 2b theory in 10 dimensions. Now, admittedly, in the correspondence, that theory is considered not in flat space-time, but on this curved manifold, and we'll come to that in just a second. Any questions? Yes?
Can you explain this counting of G mu excess symmetric tensors? So how do you get 44?
Yes, good question. So remember that I'm counting actually the physical states. Right, I'm counting the physical states by looking at the representations of the little group. Okay, so for a massless particle, the little group is 2 units fewer than the original thing. So it's SO9. So we do not count all the components of the whole metric. We just count the components under SO9. So here under SO9, it says the symmetric should be traceless, rank 2 tensor, which has that many components. And the same is true for all the other fields. I'm only counting these degrees of freedom on shell. Any other questions? Okay. Now, we will also need, although, I was going to postpone that, you can actually write down the actions of these supergravity theories. So remember, the fields for 11 dimensions are the metric, the rank 3 antisymmetric tensor, and the gravitino field. And so here I wrote down the bosonic part. So this is the Einstein-Hilbert action. This is the kinetic term for this rank 3 tensor. Its field strength is a rank 4 object, and you square it in this way. And then this theory also has a Chern-Simons term. which is a trilinear in the field A. And one of the things you have to learn when you deal with supergravity theory, and this always stopped me in the early 80s of dealing with it, is, of course, if you write down this full action, it's extremely complicated. Well, this one's not too bad, but if you go down lower, with all the fermions included, it's incredibly complicated. Now, you need, of course, to know what this action is with all the fermions so that you can check that this theory is indeed invariant under local supersymmetries. But once you've checked that, the grand realization is that most of the time you just don't really need all these fermion terms. And if you delete the fermion terms in supergravity theories, at least then you can sort of fit them on a half page or something like that. Okay. So if you go to the literature where supergravity theories are considered, use it as a guiding principle. Most of the time you really don't need all the fermion terms, and then you will be a lot happier, I promise. Now, also for the type, I will skip the type 2a theory. It's gotten by simple dimensional reduction. But the type 2b theory can also, to a large extent, be deduced from an action principle. The rank 4 tensor has a plus on it, which means that its field strength, which I'll call F5, it's a rank 5 tensor or form, has to be self-dual. You need this property because if you had also the anti-self-dual components in here, then the matching of the states would simply not work, and the closure of the supersymmetry would be violated. So this condition is an important condition. The problem with this condition is that there isn't really a covariant action principle known for it, although there is some recent work that by Belov and Moore that improves on the situation, although it does not allow you to write down a completely invariant action yet. So because of this, one has to be a little bit more careful. And so the supergravity action, again, has an Einstein-Hilbert part, kinetic terms for the dilaton and for the H field. H is the curl of B. That was in my list. And then here you have various squares of field strengths for the axion, the rank 2 antisymmetric tensor, and rank 4 antisymmetric tensor. And then there is also this last term here. And then there are, of course, many fermion terms. So the equations, the field equations may be deduced from this action. You vary all the fields, write down the resulting field equations, but those field equations will not imply the self-duality condition. You need to impose it as an additional restriction. Okay, so any questions about supergravity? Well, having done supergravity, the next topic is now string theory. Now, of course, it is not really possible to do this in 2 pages, but I will try to give you enough so that we can make some points that relate to Maldaceno's conjecture. So, of course, as you all know, you have closed strings at fixed time. They evolve, span out a world sheet. But in general, this world sheet propagates not in a flat Minkowski spacetime, although that is probably the way you started out in string theory. But in general, it propagates in the presence of some metric and also some extra fields like the dilaton and the antisymmetric tensor field. So interactions between strings, as you all know, are given by simply joining and splitting of strings. But what I really want to come to is that the dynamics of a string moving in some general background is given by a sigma model, namely by a 2-dimensional quantum field theory on the world sheet in the presence of the metric on space-time and all the other fields that are there. Now, of course, string theory has many fields. There are massless fields, but there are also an infinite tower of massive fields. The massive fields in the action would actually correspond to non-renormalizable or irrelevant interactions in the sigma model. And as a result, by using standard renormalization group analysis, the inclusion of the massive fields in the sigma model is really redundant. That's why the term irrelevant is used. They're not relevant. Their effect can always be reabsorbed in a redefinition of the fields that do produce relevant terms. So in fact, this is why the supergravity theory is so important, because it actually provides the fields that are relevant in the sigma model. The other fields will be generated automatically by string theory. So now this brings me to 2 points here. The first one is alpha prime. Alpha prime is like the Planck length square in 10 dimensions. So that's the overall coupling constant of the sigma model. And the other thing is the way that the dilaton couples to the world sheet. It couples through the curvature on the world sheet, which is actually not a conformal invariant coupling, but that's exactly what you need for the two-dimensional scaling anomaly to work out. So this is the sigma model action, and scattering amplitudes like these would be given by an integration over the positions and also over the two-dimensional metric on the world sheet. Now, the reason I brought up this coupling is that in the approximation where phi is a constant, namely the constant part of the dilaton, the constant part of the dilaton multiplies the integral of the Einstein-Hilbert density in 2 dimensions. That quantity is a special quantity. It's a topological invariant called the Euler number of the surface. And its values are given by this expression where h is the number of handles or the number of loops of the diagram, and b is the number of boundaries. So in fact, the constant part of the dilaton, through this sigma model coupling, has the effect of multiplying any amplitude by this factor. And this factor, as you can see, has a power in it, which is h, the number of loops. So in fact, this factor, if I ignore the boundaries for the moment, counts the number of loops in the amplitude. And that's, in a sense, by definition, what we mean by the string coupling constant. So the string coupling constant is nothing but the exponential of the dilaton in some normalization. Now, the last point I want to make is that conformal invariance reproduces the supergravity field equations plus string corrections. So I think you all know why we have to have conformal invariance in the sigma model. X mu is the position of the string in a space with Minkowskian signature, and that means that its time component actually has the opposite commutation relations from the space component. And if you decompose this field into creation and annihilation operators, that field will create states of negative norm. So in order to decouple those states of negative norm, conformal invariance on the world sheet comes to the rescue. And so the only way known to decouple negative norms is actually through conformal invariance. So this is very much the same reason that gauge invariance is needed when you have spin 1 fields in the Yang-Mills theory, because the gauge invariance allows you to decouple the negative norm states in the gauge field, which also is a vector and also has a time-like component here. So in other words, the sigma model is only the starting point. Really, when you want to have a consistent string theory in the presence of these backgrounds, you need to require that this sigma model be invariant under 2-dimensional conformal transformations. Now, again, one requisite for two-dimensional conformal invariance is that at least you have scale invariance in 2 dimensions. And scale invariance for a sigma model is something that we know about because it's given by the beta functions, namely the way in which the various fields depend on the renormalization scale or the cutoff. And these quantities for a general sigma model are very difficult to compute, and in general they are not known, but they can be computed in various approximations. And the most familiar approximation is when alpha prime is considered small. Okay. Remember that if you do standard field theory, the number you would have here is h bar instead of alpha prime. So alpha prime plays the role of h bar here, but the role of h bar here is played by the exponential of the dilaton. So if this surprising, well, no more than claiming that h bar is small, it's also a dimension-full parameter, we do it all the time. Alpha prime is also a dimension-full parameter, and claiming that it is small simply amounts to the approximation that we are in the low energy approximation to the problem. So in other words, an expansion in alpha prime is an expansion in the derivatives on the field transform in powers of the momenta and the energy of the fields or the states. So within that approximation, these beta functions can actually be computed because the calculation is really like in a sigma model if alpha prime had been h bar. And so by every order in the loop expansion on the world sheet, I obtain terms of higher and higher order in alpha prime. Now, these terms get very complicated, and understanding higher order alpha prime terms is a business and an art all by itself, so I will not discuss it. But what I will discuss is basically the lowest order approximation. So the lowest order approximation for the metric and the antisymmetric tensor, you actually get from a one-loop calculation, which is quite easy to do, in fact. And the first term you get is the Ricci tensor in 10 dimensions. Could be done in any dimension, but in 10 dimensions in particular. And then there are additional corrections due to the presence of the extra fields, which you can think of here as matter fields, if you wish, not gravity. And the beta function for the dilaton has a constant piece. And then of order alpha prime is a whole slew of contributions involving the Ricci scalar, the square of the field strength of B, and dilaton terms. Because the dilaton couples in a non-standard way to the world sheet, that doesn't look like it's right. These terms, there's an overall 1 over alpha prime, but the dilaton coupling itself has an alpha prime. So its 3-level contributions act as if they were one loop, which is typical for this kind of Wessomino term. And so the dilaton actually screws up a naive counting of the orders of alpha prime. So this is one loop, this is 2 loops, and so on and so forth. A little bit changed. So, of course, here you can immediately see that D has to be 10 for this term to vanish, the leading term. And then the other equation, now of course there are other equations like the beta function for the antisymmetric tensor field, which I did not exhibit. They are very similar. So conformal invariance requires that all these things be equal to 0. And in particular, this equation is in fact the generalization of Einstein's equation, including the antisymmetric tensor and dilaton fields. And this equation is exactly the one that corresponds to the type 2a or type 2b supergravity field equations, provided certain fields are set to 0. And they correspond to the Ramon-Ramon fields, and I will not go into that. So, roughly speaking, to summarize, the leading order alpha prime requirement of conformal invariance actually gives you the field equations of supergravity in 10 dimensions, and, well, needless to say, requires that dimension is in fact 10. And so string theory can be viewed as simply the fact that these beta functions receive higher order corrections in alpha prime. Any questions? Here is that supergravity is the low energy approximation to string theory, and this comes out of the conformal invariance requirement of the sigma model. Any questions? You're all with me, okay? Well, for having done string theory in 2 pages, that's going pretty well. So now we will move on to the states that string theory contains, and also supergravity. So of course, supergravity, and let me talk about supergravity to be specific. Supergravity contains the states that I had on my big transparency. Yes?
Yeah, I have a question. So, I'm not a string theorist, but I have the impression that the string theory is supposed to have some, this M theory that contains all of these different string theories.
Mm-hmm.
So, when you say that the Maldacena conjecture is about a theory being dual, it's type 2B string theory, what does that really mean?
Well, what I have done is I have given you one version, okay? The simplest and original version of the Maldacena conjecture. Later on, I and other speakers will extend this beyond this, because in fact, this theory is very restrictive. It has to be with maximal supersymmetry, and it has to be conformal invariant. Well, the theories of the world are not maximally supersymmetric. In fact, the world is not even supersymmetric, and the world is certainly not scale invariant, okay? But nonetheless, this context can be generalized later on. Well, it can be generalized. And so later on, we will see that you can lower the degree of supersymmetry. You can give up conformal invariance. And then the equivalence is not exactly with this, but it will be, for example, if you have theories that you get by breaking the supersymmetry here, breaking the conformal invariance, these theories will be given by deformations of these manifolds. So type 2B on those. But then there can be whole different classes of theories in which here we have not type 2B theory, but actually M theory. Okay. So the second part here could actually be M theory on certain other manifolds, like, for example, AdS4 cross S7 would be the simplest one, and AdS7 cross S4. But the theories that correspond to those are respectively 3-dimensional conformal field theories, 3 in the sense of 2 plus 1, or, 6-dimensional conformal field theories. Both of which are very ill understood, actually. You would think that by lowering the dimension you gain. But 3 dimensions is an odd dimension, I mean, obviously an odd dimension, but odd in the sense of unusual dimension. And supersymmetry is not as powerful there, and so, there's not that much you can say, although many people, including myself, have, not let that stand in the way of a paper. So, in fact, here, you could have all kinds of different theories. I'm just giving you essentially sort of the most the most supersymmetric case.
I guess I'm still kind of confused. So you're saying that you can generalize that duality to some other cases where you would say it's M theory.
Right.
But I don't know, what does it mean to say that it's not M theory? I mean, if type 2B string theory has to be incorporated in M theories, then what would it mean to say that the theory is dual to only type 2B string theory?
I'm not sure I entirely understand. I mean, type 2B theory is some limit of M theory somewhere. So it's contained in there.
Does type 2B string theory sort of exist and non-perturbatively be a part of it?
No, it doesn't have to be part of M theory. It can exist all by itself. In fact, as you saw from, well, it's not on this transparency, but type 2b theory also has this SL2Z duality, in which I interchange weak and strong coupling. So you can see that it's its own strong weak coupling dual. You don't need to go to M theory. So, right, so, you know, forgive me for presenting only one case here in a way, but I wanted to be specific, which is hard to do if you mix dimensions and supersymmetries. But later on, in the last lecture, I will give you an example of where things change. Yes?
So I had a question based on his question. Maybe that's what he's asking, that if you have a dual theory, I mean, M theory contains, or type 2b theory in some sense. So shouldn't there be a dual theory which contains all of these other dual theories instead of the dual theory should reduce into the other smaller dual theories in that sense, I guess.
I guess so. Right. Yeah. Any other questions? Let's see, where was I? Oh, yes. So basically, we have, of course, given a list of all the states that are perturbatively in type 2a, type 2b, or 11 dimensions. But quantum field theories contain states that are other than perturbative. And so this brings me to brane solutions. So in fact, in all of these theories, we have seen that there are certain antisymmetric tensor fields of various ranks. So let's call it P. So by A here, I denote the field potential, not the field strength. The field strength is D of A, if that's what the field strength is. So actually, all of these antisymmetric tensor fields have the property of a volume form in dimension P. And so in fact, they naturally couple to manifolds that have dimension P. Just like the way you can do electromagnetism a la Feynman by having a particle propagate along a world line, and then the way electromagnetism is coupled is simply by integrating the gauge potential along that world line. Okay, so the gauge potential, which is a one form, naturally couples to a one-dimensional space-time object. So this is a generalization of that. So in fact, the action for that coupling is simply given by taking this P form potential and integrating it over the P-dimensional, but this is the space-time dimension of this space or subspace. So in particular, well, the one form I already explained, it's dual to a particle. We also had an antisymmetric two form, the B field. Well, that naturally couples to a string, as we saw from the action for the nonlinear sigma model, and so on and so forth. Now, also, each field actually has a magnetic dual, which we'll call A tilde. And the way that's defined is, first of all, you compute the field strength, which you obtain by applying D to AP. He knows what that is, right? So it's the volume form in the complement of P plus 1 dimensions. So this gives me a form of dimension D minus P minus 1. And it is naturally the D of something, namely the D of a potential, which is called the magnetic potential. So now, having this duality, we know, in fact, from the field content of the various supergravities that we discussed, what the content should be for these various extended objects, or p-branes. So for example, particles. Well, in type 2a, we had encountered the graviphoton. That's one form. So it naturally couples to a particle, which is the D0 particle. That 0 refers to, right, this nomenclature is a little bit off, you know, because the number here, the p-brane actually refers to the space dimension. So this is called a D0 particle. And its magnetic dual is is a 6-dimensional extended object. So in terms of the 2 form, which we have for both type 2A and type 2B, the B field, this is dual to the fundamental string, a 1-dimensional object. For type 2B, we actually have a second rank 2 antisymmetric tensor, and its dual object is the D1 string. And then we have 3 forms. For 11 dimensions, we had a 3 form. So this is the M2. This is a membrane, 3-dimensional space-time object. We also have this for the type 2A theory. And finally, for the type 2B theory, there's a rank 4 antisymmetric tensor. And it couples to a 4-dimensional space-time object, which is a D3 brane. And in fact, the D3 brane, if you compute its magnetic dual, it's exactly D3. It's invariant under this generalized electric magnetic duality. So, of course, these objects are to be, they will become, at least the ones that have a D in front of them, will become the D branes that one can study using conformal field theory, and which were invented by Polchinski a little bit more than 10 years ago. But basically, just by considering the objects that can couple to the various fields, we already know which quantities of which dimension should in fact be present in the theory. Let's see. Okay, right. So actually, that's basically, that was an argument of quantum numbers. Now you can in fact ask, well, if the quantum numbers are given, then can one in fact find solutions to the supergravity theories with those quantum numbers? And basically, they are always realized as half BPS solutions, namely solutions with 16 remaining supersymmetries. So these are the D branes. So I want to give you a little bit of an idea what these supergravity solutions look like. So we imagine that we have a P brane in D space-time dimensions. So you can think of this object as flat, okay? And it has, right, so here it is. So we can split the coordinates into the Minkowski P coordinates of the brane itself, parallel to the brane. These are the coordinates x0 until xp. So P here, by the way, is now going to denote the space dimension of the brane. I should really, on the previous transparency, have written P+1, but that's okay. So these are the coordinates parallel to the brane of dimension P+1, and then the remaining coordinates are perpendicular to it. So there is a natural distance, which is the distance from the brane, gotten as the distance of these transverse coordinates. And now we can look for a solution in supergravity that has maximal symmetry. That's always the easiest solution to find. So in fact, along the brane, we can require Poincare invariance in P+1 dimensions, while perpendicular to the brane, we require rotation invariance in D minus P +1 dimensions. So that's the symmetry that I've written down here. In these two lines here. So this is the ansatz. And now we are to plug this ansatz into all the field equations of type 2B theory. Okay. Well, recall what the field equations, let's see what I can find. Right. The thing I want to draw your attention to is that in the string metric convention, there is a dilaton factor out here in front of the Neveu-Schwarz fields, but there is no dilaton factor in front of the Ramond-Ramond action. This is a crucial difference, and it comes about from string theory or simply from the way supergravity is put together. So in particular, that means when we write down Einstein's equations, and I'm neglecting, of course, all string states here, it has a contribution of the Neveu-Schwarz 2-form field strength, which does not have a factor of the dilaton in front of it. And then it has all the Ramond-Ramond fields, namely the axion, the 2-form, and the 5-form, but they now all have an exponential of the dilaton in front of it. And remember that the exponential of the dilaton was the string coupling GS. So you see that the strength by which the various fields couple to gravity differs depending on what their nature is. If they're Neveu-Schwarz, there is no factor of the string coupling, while if they are Ramond-Ramond, then there is. So, okay, well, I don't want to go through all of these things, but so the brain is located at r equal to 0. R, remember, was the distance from the brain. And the flux of the field provides the source for the existence of the brain. So now here's the typical solution. The typical solution for the metric is the Minkowskian metric on the coordinates parallel to the brain, multiplied by some function h to some power, and then plus the distance square away from the brain, perpendicular to the brain, multiplied by the same function h, but to another power. All the solutions are, in fact, of this type. Now, because these solutions are, in fact, half BPS and supersymmetric, h is a harmonic function, always, for all cases, in the transverse dimensions. So that's rather easy to solve, because now we've reduced the problem to a linear problem. So h is a harmonic function in dimension d minus p minus 1. And so you can write down, on general grounds, you can write down what its solution is. The 1 is here because asymptotically, we'd probably want to have a Minkowskian space-time that's flat. Okay. And so that means that asymptotically, if these powers are positive, this goes away, and I just have a 1, so that the metric is indeed the Minkowskian flat metric. Yes?
Are these metrics string or Einstein?
I think these are all, in type 2b, these are all Einstein. Well, okay, since I'm sort of doing this very generally, in type 2b, there's certainly Einstein frame. In M theory, there's no distinction. And in type 2a, I don't remember. But we're not really considering much stuff in type 2a.
But without specifying what P1 and P2 are, what does it mean to say that it's Einsteinian?
I'm sorry?
Without specifying what P1 and P2 are, what does it even mean to say whether it's Einstein? I mean, we know that P1 will turn out to be minus half and plus half a string frame.
Yeah, that's a good point, right? So at this point, you know, whether you are dealing with the Einstein frame or the string frame would give you different powers of P, essentially.
But that action wouldn't
I had written the action in the string frame here. Yeah. Yes, that's right. When you actually, and sometimes it's more convenient to use the string frame or sometimes the Einstein frame. In type 2b, it's going to be very convenient to use the Einstein frame for a reason we'll come to later. Any other questions? Okay. So now, what is this number here? There is a number here. This number is going to be important. Well, first of all, R has a dimension. So there's an alpha prime to a certain dimension that comes in to make this object dimensionless. But then, if we have DP branes, namely if it is the Ramon-Ramon fields or charges that are turned on, then this number has an extra coupling constant in front of it. While if we have NS or M branes, then there is, well, in M there is no coupling constant, so then there is no such factor. It's just a number of order 1. So this difference has an important consequence. Let's see. Right. Yeah, which I guess I'm going to explain only in the case of the D3 brane, but it's true generally. So I guess now we're coming specifically to the D3 brane. So the discussion of the previous section completely applies. The D3 brane is a 4 space-time dimensional object, and we're interested in a metric that's that has Poincare symmetry in 4 dimensions, and then we have 6 transverse dimensions. So it is invariant on the Poincare symmetry and SO6 in the transverse space. So what if the solution corresponding to the D3 brane? Well, it has constant dilaton and axion fields and vanishing rank 2 tensors. And the rank 5 antisymmetric tensor field is actually proportional to the volume form on the sphere around r equal to 0. Remember that the transverse space is 6-dimensional, and r is equal to 0 is the position of the brane. So by foliating as a function of constant r values, I have a sequence of 5 spheres. And this epsilon is the volume form on that. And then by dimensional grounds, there has to be an alpha prime in front of it. And there can also be some numerical factor, essentially. But this numerical factor must be an integer, because the flux on a 5-sphere is generated by an integer cohomology class. And so this number has to be an integer. And the metric is of the following form. As promised, it's of the form of an h to some power and h to an inverse power. And in the case of a D3 brane, you can use the previous formulas. This function h for a single brane will be 1 plus r to the 4th over little r to the 4th. And capital R to the 4th is some constant, which can be determined from the general solution. And remember that for a D brane, it was proportional to GS, to the string coupling, and then also to alpha prime square. So the reason I've been insisting on the presence of this string coupling is because as you take the string coupling to 0, let's say with alpha prime and n fixed, we can see what happens. Well, if GS goes to 0, then basically this capital R becomes very small. And so essentially the metric away from r equal to 0 becomes like Minkowskian metric. This perturbation r only sets in when little r is of order capital R here. But if capital R goes to 0, then basically anywhere except on the brane, space-time is really flat. So effectively, the D3 brane then becomes a screen. And it is for this reason that we can treat this extended object with the help of conformal field theory. Because in fact, it is in the GS going to 0 limit that we treat this object essentially as a planar defect, and we can describe the sigma model on this in the presence of this solution with the help of conformal field theory in the presence of the boundary. So that's of course how D branes were originally discovered, was by requiring Dirichlet boundary conditions on open strings that couple to these defects. But now you also see from the supergravity point of view why, in fact, that's a very reasonable expectation. And this is true for all D branes. Yes?
So when you say it's a reflecting screen, what should I understand how that means? Reflecting, because that's the horizon, right? Arguably 0.
I'm not quite sure why I wrote that reflecting. So let's just delete it. Okay. Right. It's one way of dealing with a question. Okay, so now we have the D3 brane. Now we understand why it can be treated in perturbation theory or in conformal field theory. And so finally now I am ready to move to the context of the Maldacena conjecture. So there is one more thing that we need to do, and that is not to have just a single D3 brane, but in fact a stack of D3 branes. Now recall that a single D3 brane, I didn't quite show it, but it is true that it is half BPS, it preserves 16 supersymmetries. If we actually stack several D3 branes in parallel to one another, then that amount of supersymmetry is preserved, and the whole is still a half BPS solution to the supergravity equations. Okay. If, on the other hand, you twisted the angles of some of the D3 branes, that's not true. Then you will break some of the supersymmetry. So it is essential that we keep these things parallel. Now, each of the D3 branes actually has a U1 gauge field on it. This is not something I can show in detail, but it results from the presence of these antisymmetric tensor fields. And so each of these things has a U1 gauge field, which sort of makes sense since you can have these open strings ending on it. So if I have an assembly of n parallel D3 branes, then of course each of the D3 branes by themselves carries a U1. However, I can also have open strings spanned between one D3 brane and another. Okay. Now, the length of that open string is essentially proportional to the mass of that string, or the difference of Higgs expectation values. But it's essentially a mass. So these strings are massive. So what we really have is U1 to the n gauge fields and massive strings between them. So this is a little bit like massive W bosons if you were thinking of doing some phenomenology ahead. But in fact, if we take the distance between the branes to be smaller and smaller, and in the limit take the n D3 branes to be coincident, then you can see that the length of all these strings actually goes to 0, or at least the minimum length of the string goes to 0. And so what happens is that the W bosons become massless, in fact. And these massless W bosons, together with the U1 gauge fields, actually form or build up the full group SUN. In other words, the U1 fields you can think of as corresponding to the Cartan generators of the group, and then the massive bosons that become massless you can think of as the roots of the Lie algebra. Now, you would think there is a U1 also, but this U1 is the overall center of mass behavior of this assembly and effectively decouples, so we can forget about it. So in fact, now what we have seen here is that if you have an assembly of n parallel D3 branes, then naturally that assembly supports an SUN Yang-Mills theory that lives in 3+1 dimensions, and which has n equal 4 Poincaré supersymmetry. Well, I don't think I'm going to be able to finish today, but that's fine. Just go on tomorrow. So now that we've acquired all this, we're actually ready to we're actually ready to discuss the Maldacena limit. So the setup is as follows. We have n coincident D3 branes. And in fact, one can write down the metric corresponding to that solution. Now this number n has genuinely become the number of the D3 branes. So if little r is a lot larger than capital R, then the limit is simply 10-dimensional flat space-time. That's because the only term that changes that actually goes to 0. Now it looks at r equal to 0 like we have a singularity. But in fact, this is not true. When little r is very small, okay, then we can essentially drop this 1 here. So this is now the behavior. And you see that this metric sort of magically takes on a different form. If we drop the 1, we take the square root here. We have capital R square over little r square. So we bring out an overall r square. The 1 over little r square cancels this one. The metric of the 5 sphere is isolated, separate. Then we have a term in capital R square, dr square over r square here. And finally, this term becomes simply this term. So the first term is all by itself here. Capital R is a constant, and this is the metric on the 5 sphere. So that's fine. And this metric here looks singular, but in fact, by making a change of variables from r to 1 over r, which we call u, we put it in the following form. And this expression is actually a canonical way of representing hyperbolic space. It is a space that is conformally flat and in fact conformally equivalent to Minkowski space, at least locally. So this space is also 5-dimensional. This was 5-dimensional. This is also 5-dimensional because mu ran from 0 to 3, and then we have an extra coordinate. So this space is actually AdS5. It's the Minkowskian, this has Minkowskian signature. It's the Minkowskian version of a hyperbolic space, and it has negative cosmological constant. So this is in fact the Maldacena limit, and this explains why the equivalence of SUN n equal 4 gauge theory is with string theory on this manifold, AdS5 cross S5. That's where it comes from. It's in the near horizon limit that this space emerges. Let's see. In the 1 minute that remains, let me discuss the correspondence of the various parameters. So let's look at this. So if we keep the string coupling and the number of D3 branes and all physical lengths fixed, but let alpha prime go to 0, then in fact, this is like letting r, capital R to the 4 go to 0. Okay. But that is exactly what am I saying here? Right. So that is exactly the limit in which this 10-dimensional flat region decouples. So if you are looking at a typical physical quantity like the effective action, well, it will have an expansion in powers of alpha prime multiplied by the Ricci tensor scalar, Riemann tensor, and so on and so forth to certain powers. In the limit where little r is much larger than capital R, these objects simply by scaling behave like 1 over little r square. So in that limit, the contribution to the Lagrangian actually vanishes. So the flat region, in fact, decouples when this limit is taken, and only type 2b on AdS5 cross S5 remains. So, I haven't quite finished with lecture 2, but I have finished lecturing for today, I think, since I run out of time. So I will continue next time. Any questions?
I'm a bit confused about this physical length fixed. The way we measure physical length is obviously in comparison to something else.
Mm-hmm.
The only thing to compare here is L blank or LS, which is the same in this case, because it's equilibrium. So what do you mean by saying physical lengths are fixed?
Well, basically, I'm thinking mostly of little r, in a sense, as a physical length, okay? The parameter, right. And if I had other length scales in the problem of that same ilk, I would keep those fixed. That's sort of the notion. Any other questions? Okay, well then we'll continue tomorrow.